Again, welcome to Signals and Systems. This is Learning Outcome 1-1. Give examples of signals and systems. The name of the course is Signals and Systems. We're going to start off the semester with a discussion of what are signals and what are systems. I'm going to give you two definitions of signals taken from typical EE books. Here's the definition. Signal: a time-varying physical phenomenon which is intended to convey information. The other definition is a function representing a physical quantity or variable, and it typically contains information about the behavior or nature of the phenomenon. Both these definitions talk about physical phenomena. They don't need to be physical phenomena to be signals, but they quite often are. So these definitions are not complete, but they do provide a good place to start. One thing that is very important is that it is a function. That goes back to prerequisite knowledge for this course. What is a function? It is something with an input and an output, an independent variable and a dependent variable. In this course, the independent variable is always time. It doesn't have to be time in general, but for this course we'll keep it as time. I teach a follow-on course on image processing. There, the independent values are spatial X and spatial Y. And in videos, it would be spatial X, spatial Y, and time T. We'll keep it simple with one variable, time. The dependent variable is what we're trying to measure. In a circuit, that could be voltage or current. In a mechanical system, that could be pressure or force. Signals can be in continuous time. We use the variable t for time, continuous time, and for notation, we use round parentheses. This is not universally used, but is used by the majority of researchers. We can also have discrete time. Then our time variable is n instead of t, and we use square brackets to help denote this. Now you're familiar with functions of time. For example, x of t is 3e to the minus 2t u of t, where u of t is a unit step or Heaviside function. You can imagine that there are functions of n, and you may have seen them, but a function like this is not something you've seen very often. Therefore, we're going to do a lot of work going back and forth between the two domains, using t where you're more familiar, and then n as its complement. We live in continuous time, but because of computers, we have an awful lot of work that was discrete time that you as an engineer need to know how to use. The concepts are the same, and we'll work with both throughout this course. Also consider this, a differential equation in continuous time. You had a whole semester of this in your differential equations class. And hopefully you have a fair amount of knowledge of how to work with these. Here's an equation for what you would see in a discrete world. Here we have time delays instead of derivatives. If I gave you this, you'd have a lot harder time working on it today. But by the end of the course, you know how to work with those. And again, because of your familiarity with the continuous time, we'll do a lot more work in continuous time and then eventually swap over to discrete time, hoping that by the end of the semester you'll be comfortable with both and have skills for both. Notation. We said that a signal could be an input signal or an output signal. For input signals, we use the letter X. We use x of t for continuous time and x of n for discrete time. Our output signal, we use the variable y, with y of t for continuous time and y of n for discrete time. Remember that, x for input, y for output. That's going to be a big hint for you as you work on problems. Now we'll talk about a system. What is a system? A system is a device that has an input and an output. The inputs and outputs are signals. That's useful since we just talked about input and output signals. We quite often diagrammatically describe it like this, showing x of t going in to some system and y of t coming out. It could be in discrete time with x of n and y of n. Here are 8 examples of systems. Some of them, such as number 1, number 8, are circuits, and since circuits 1 and circuits 2 are prerequisites for this course, you should be fairly familiar with those circuits. Other ones are mechanical systems, like 2, 3, 5, and 6. 7 is a mixture of the two. 4 is an economic system. Let's think about this. If this were our system, what are the inputs and outputs? The input is our voltage, and the output could be a current that's flowing through your circuit, or it could be the voltage across your diode or your resistor. The physical item, the circuit, is your system. The current and the voltage are things you measure, which would be your signals. Another example, suspension system. Here's your system, the physical object. Your signals are things you measure going in and going out. You can measure the amount of electricity being applied, the amount of torque being applied, and likewise you can measure the speed of the wheels going out. There are many possibilities within the system as to what you choose for your input and output signals. It depends on what you're trying to accomplish. Another mechanical system. Again, the physical object is your system. Signals are things you can measure. So what can you measure? You can measure the amount of fuel being provided. You can measure the speed at which it's traveling as your output. Try and think of some other examples of what could be an input or an output signal for this particular system. Here's the example of a financial or economic system. I said that not all systems have to be physical systems. Talking about things that could be input, input could be a money supply, amount of money. An amount going out, your output signal, could be an exchange rate. It could be an amount being spent on some products, amount of money within a financial institution. There's a lot of things. In America, the majority of American students getting a PhD in economics actually have an engineering bachelor's degree. This here comes from one of my past jobs. This is a ship, and this spool in the middle is a towed array, basically a garden hose full of microphones to listen to what's going on in the ocean. You could think about the ship having a speed. You can think about how much of the towed array is being trailed out as one of your input signals. The speed of your ship could be an output signal if what you're trying to accomplish is to get motion from the ship. Or you could look at the electronic system of the array, and your output could be what is measured for sound in the ocean. Here's another system. Think, what is the physical system? And what are the possible inputs and outputs? I'm not going to tell you. And another one, an audio system. What are the inputs? What are the outputs? Things that you can measure. And again, another circuit. What's going in that you can measure? What's going out that you can measure? Welcome to a whole semester of signals and systems. I hope you have an idea now of what is a signal and what is a system.